In the last video, we started talking about the volume of solids of revolution. So let's take a look at page 639 in the notes and start looking at the mathematics behind this. All right, so here's an example where we're going to take this probably parabola shape and we're going to spin it around the x-axis. And so it's going to look a little bit like this. It's going to be kind of wide, a little bit wide. It's going to narrow down as it gets further, and then it's going to flare out. So this is going to look a little bit like maybe a fancy flower vase, except that this is totally filled in. This doesn't have any space in it because it's this entire area that's being swept out. And so when we want to calculate the volume of this figure, we're going to do this a little bit like what we were doing at the beginning of the semester, where we wanted to find the area of this. And so what did we do to estimate the area of this figure? Well, what we did is we kind of drew some rectangles. And we said, well, I can calculate the area of these rectangles. And so all of these rectangles together are kind of close to the area of this shape. And the more rectangles I do, the better the estimate's going to be. So we're going to do the same basic idea, except that we're going to think about rotating this rectangle around the x-axis. And what kind of shape are we going to get when we do that? This was the first example we talked about in the video that we just watched. So as a rectangle rotates around an axis, it's going to create a cylinder. All right, so that's going to be a cylinder that looks, I don't know, a little bit like this, I suppose. All right, and just like we were able to calculate the area of this rectangle, we're going to be able to calculate the volume of this cylinder. So the volume of a cylinder is equal all three-dimensional prism shapes, like a box or a cube or something like that, is going to be the area of the base, which in this case is a circle, times the height. All right, and so the area, since it's a circle, is going to be pi r squared times h, where r is equal to that radius and h is equal to the distance between the two circles. Okay, so when we're putting it into, when we're estimating that, I want to kind of change this around a little bit. So if we were to take a whole bunch of these rectangles that were all the same width, what we would do is we would find that the sum of all of those disks was the sum of pi times f of x, because that's the radius of the circle, is the height of the triangle, which is f of whatever our value is. And that's squared times the height. And the height here is, like we say, it's going to be some delta x. It's going to be the same value for each one. So this is the estimate that we get from using 8 rectangles or 20 rectangles or 100 rectangles. It's going to just give us an estimate. And the same way that we got the actual value from this, by using an infinite number of rectangles that were all incredibly tiny, and then expressing that as a definite integral, we've got the same thing going on here. We've got the definite integral from the start to the finish of pi times f of x squared. Instead of delta x, it's going to be dx. So we're going to represent this as a definite integral in order to find the volume of all of those cylinders, which is going to be the volume of the solid of revolution. All right, there are a couple things that make this look different from what is here in the notes. The first is that they took this pi, which is a constant, and moved it outside of the integral. And the second thing that the author wanted to do is he wanted to say, okay, well, this is cool if we always want to rotate around the x-axis, but maybe sometimes we don't. Maybe sometimes we want to rotate around this line down here. All right, and if we do that, we're going to get kind of a vase shape like this, except it's going to be bigger and it's going to have a large cylindrical hole in the middle because this part is not a part of the shape. All right. And now, before we get into any examples, he wants to add an extra twist into it, which is what happens. Let's add in the thing we did in the last couple of videos, which was talking about the area between two curves. And so if we want to take a shape which is the area of two curves, like let's say I wanted to rotate this shape around the x-axis, what we would do is we would rotate the outer shape around the x-axis and we get that volume. And then we'd rotate the inside shape around the x-axis, and then we'd subtract those two volumes to represent that we would have this cylindrical hole in the middle of this vase shape. Okay, so that's just basically what all of these formulas on the first page are talking about. And in the next video, we'll start to take a look at an example and see how we're actually going to do the math in order to calculate this.